It feels like we have been on this handout forever, doesn't it? We're finally going to get to the last set of exercises here. We've so far found vertical asymptote lines, holes in the graph, intercepts, then we found horizontal asymptote lines, and asymptote lines actually can be slanted lines, right? There is such thing as a slant asymptote line. Not sure if you've ever heard of that before in the high school curriculum. Now, let's say this. A rational function, all of these that we've been working on this paper have been rational functions. A rational function is the ratio of two polynomial functions. A rational function will have a slant asymptote line if and only if the degree in the numerator is 1 higher than the degree in the denominator. So we have seen that our, quote, top-heavy rational functions did not have a horizontal asymptote line. You won't have a horizontal and a slant asymptote line. Okay, that'll never happen. So while you're copying down, I'll make a note that this is our top-heavy scenario, although it has to be top-heavy by only 1 degree. Okay, so what's a slant asymptote line going to look like? We know what a vertical and a horizontal asymptote line look like. A slanted line looks like this, right? It's going to have a slope and it's going to have a y-intercept. So how are we going to figure that out when we see a rational function? So the 3 rational functions shown below. And you know what? I just realized there is a typo here. This should just say f of x equals. I don't know why I have the limit there. I just realized that. F of x equals this, because we're actually not finding the limits to infinity. We would be doing that if we were finding the horizontal asymptote line, because actually if I tried to find these limits to infinity, they would also be infinity, right? Because it's top heavy, because the number of cookies is growing faster than the number of people showing up to eat the cookies, all right? So all of those limits would actually be infinity. Right? So we're actually just looking at these 3 functions and they're all going to have a slant asymptote line. All right, so how do we figure that out? And we should know that this line here, right, means divide, right? If you saw this and you wanted to know what that really was, right, you'd go like this. Okay, so we're going to do that same exact thing. We are going to, for this first one, divide x plus 2 into x squared plus 7x plus 1. Okay, so how many times does 2 go into 7? In other words, or 3? How many times, what can I multiply 3 by to get me close to 7? And it would be a 2, right? So what can I multiply x by to get x squared? The goal in synthetic division, or polynomial division, actually this isn't synthetic division, it's polynomial division. The goal is to always make the first term 0 out. And so actually I could, x goes into x squared x times. See how I started putting it here? The x here, that would be incorrect. We want to line up by place value. Okay, so this is the x's place right here. So I want to put the x right over here. All right, and then I do x times, just like here I do 2 times 3 is 6, right? And then I subtract and get a 1. I do the exact same thing. X times x plus 2 is x squared plus 2x. Okay, now I subtract. Okay, so the goal is always to make your first term zero out when you're doing polynomial division. So when I subtract this, put subtract and then parentheses, okay, I get 5x, and then you have to bring down whatever is left. So say I were doing 3 into 45, right? I'd go, okay, 3 goes into 4 one time, right? And then I subtract and I get a 1, and then I bring down what's left, right? That's how we do regular old division, okay? So here I have to bring down the +1, okay? Then my goal is to say, what would make the first term zero out, okay? And that would be if I could put a 5x here, right? I want to get a 5x here so that the first term zeroes out when I subtract. So in order to get a 5x here, I'd have to multiply by 5, positive 5, right? So it's +5. And then I'd get 5x when I multiply, just like over here. You know, when I get a 5, I multiply 5 times 3, and that's 15, right? So same idea over here. What's 5 times x plus 2? Okay, that's 5x plus 10. And then in this case, I get a remainder, right? I know I'm done because if I've lined things up place value wise, once I get to the edge of this bar, I am done, right? Because the degree here, when I get -9, because remember I'm subtracting this, when I get -9, I can't put x into -9. So I could write my remainder as -9 over x plus 2, right? It would be the same idea I might use over here where I get a remainder of 1 when I'm doing 3 into 7, right? So then I would write my answer as 2 1/3, okay? But here's the good news for slant asymptote lines. I have determined what my slant asymptote line is by just looking at what I get for the quotient, and I get to ignore the remainder. Okay, so that's kind of nice. I don't have to worry about the remainder. So here is the equation of the slant asymptote line, y equals x plus 5. So as I mentioned before, one of the things that I am teaching teachers when I teach people how to be math teachers is we talk about the benefit of multiple representation so that you will understand better when you look at something both algebraically and graphically. So I'm going to graph this function at the same time that I graph the slant asymptote line, just so we can look at it and hopefully get a better understanding of what's happening. Okay, so my slant asymptote line is y equals x plus 5. And then, oh, I'm on a weird zoom from the last example. So let's come over here. Just this. I love how easy it is to adjust the window. It is not so easy on the 84 as it is here. So look at that. This line in the middle is my asymptote line. I don't know why they didn't color it differently. Why is that? Usually they give one a red and one a blue. I don't know why they're not doing that for me now. They're both red. But anyway, this line here, we can see how that function gets closer and closer to that line, but never touches it. And we can see that from this direction as well. Okay, that this line here in the middle, and again, it's the end behavior of the function. It doesn't start right here in the middle, right? It's the end behavior. As time goes on and on, this function gets closer and closer to that slanted line and never touches it. So let's do one more together, and then the third problem will be left for participation work. So let's take a look at letter B, which asks me, actually, you know what? I'm going to let you do letter B. I'm going to let letter B be the week 5 day 3, even if this video falls on day 2, which it might. I haven't listed them up there. This will be the day 3 classwork. Okay, so let's do letter C together because that one is more difficult. Okay, so in letter C, why don't I get a whole fresh page? I am going to divide, I'm going to put x squared plus 8 and divide into x cubed minus 2x squared. Now you have to use placeholders because there's no x term and there's no constant term. So what you would do is you'd put plus 0x plus 0. Placeholders are very important when we do polynomial division. All right, and I have to hold my place because then I know when I get to here, once I get to here, I'm done. Okay, and I don't have to worry about the remainder when it comes to finding the slant asymptote line. So then I ask myself, what do I need to multiply x squared by to make x cubed 0 out? All right, and I would need to multiply by an x, right? That's not too hard to figure out. Now line it up in the appropriate spot. This is the x place. Okay, so I don't want to put x over here. I want to line up by place value. Okay, when I multiply x times x squared plus 8, then I would get x cubed, and then I would get 8x. I have to line up my like terms. All right, so when I multiply by x, I actually get a 0x squared, if you will. Okay, so put that placeholder in. Now I have to subtract this. Okay, but I have, so this will 0 out. That's the goal. Always make the first term 0 out. Then when I subtract here, I am going to get negative x squared, or negative 2x squared. And then negative, I have to distribute that negative. So I'll have 0x minus 8x, which is minus 8x. And then when I go to bring down the next term, right, I'm just bringing down a 0. But that is my next term. So then I look at this and say, well, how do I make this 0 out? I need to have negative 2x squared here. Right, so that when I subtract it, right, because I'm going to be subtracting whatever I put here, so that when I subtract that, my first term is 0. My first term has to be 0. I've said that like 4 times now, so I'm hoping I'm beating that into your brains. Okay, so what would I need to multiply x squared by? And I hope you could see it's a negative 2, so I put minus 2. Okay, then I multiply this whole expression by negative 2. So when I distribute the negative 2, I'd have negative 2x squared, and then I would have minus 16, right? I would actually have no x term, so I'll put a 0x here. Okay, so when I distribute that x and subtract, this would be 0. This would be negative 8x minus 0x, which is just negative 8x. And that, when I distribute the negative, becomes plus 16. Okay, but I'm done, right? I can't put x squared into x. There's nothing I can multiply x squared by to give me this. Okay, so I do have a remainder, but remember, I don't have to care about my remainder, right? So this would be my remainder. I could take this remainder and put it over the divisor, just like I showed you on the last page with dividing fractions. I can go like that. And if you do take Calc 2, there's a place in Calc 2 where you have to divide polynomials and consider the remainder. But for slant asymptote lines, I'm not even worried about this. Okay, so the equation of my slant asymptote line is y equals x minus 2. And I encourage you to graph both the original function and the slant asymptote line. And I'm going to put SA, right? Because I called vertical asymptote lines VA, horizontal asymptote lines HA. So I'm going to put SA for that equation. All right, so you've got the third one to do on your own.